has kept on changing, right? And naturally, there has been, given the importance of analyzing data, there has been many different strategies to deal with it. And these have come up, right? And these might be parallelization in terms of the CPU or in terms of the GPU, right? If the computation is what you're mainly concerned about, or it would be the distributed setup, right? If the I/O headache is what you're mainly concerned about. However, what is important to note is that each of these strategies to deal with big data come with their own set of resource bottlenecks and require either tweaking existing algorithms or coming up with novel ones that can exploit the platform, right? If you think about it a little bit, for instance, if you're working on GPU, right, then coming up with algorithms that are amenable to GPU to sort of be parallelizable by GPU. Specifically, if you're in a multi-GPU setting, right, how do you sort of write algorithms that effectively use the computational power that you have brought in, right? That's not a trivial question. Similarly, if you're working in the distributed setup, right, then coming up, if you're working in the distributed setup, then coming up with algorithms that can effectively exploit the distributed setup, right? That's also not an easy question, because at that point, communication between the servers becomes bottleneck, not necessarily the computational power or the memory constraint. Okay, and here's an alternative view to this kind of data analysis. What if we didn't need to do all this, right? What if we could instead reduce the data, right, and use whatever we have refined over decades, use our existing algorithms in order to sort of run these, give us the result. Well, of course, there has to be some trade-off, right? We don't want to say that we're going to get exactly the same algorithm, same result, even if we are reducing the data dramatically. Right? But perhaps not all data is useful anyway. Perhaps most of the data you can afford to throw away and be fine with it, mostly. Here's the roadmap at the top. I'll give a brief overview of what coresets are. I'll talk about two new results one on coresets for tensor factorization and introduce the problem. And another one on coresets for what is known as Bregman clustering. Right? This is a generalization of K-means clustering that you might already, all of you have seen. Next, I'll talk about another set of results on how to deal with coresets for optimization problems with constraints. Specifically, what happens when we have regularizations in my optimization problems, right? Yeah, what kind of effect can I imagine will have the regularization will have on the coresets, right? And furthermore, a more interesting setup will be that of a data-dependent constraints. I'll explain these as I come on. Right? And this will have some implications on machine learning algorithms for fairness problems. Okay, let's see. What do I mean by coreset? And here's a very, very high-level definition of it. I've tried to limit the number of theorems and mathematical formulas as much as I can. Here is what we mean. Suppose you have A is an optimization algorithm, right? And B is your data set. Here is the question that we're broadly asking for. Can I find a set C, right? A set of data points, right? Possibly a weighted set of data points, such that running the algorithm on C will give you roughly the same result, roughly, and define this more formally, will give you roughly the same result as running the algorithm on D, right? And often C will be a subset of D, but this is not always the case. And coresets have been researched from many different angles, and I don't want to sort of restrict it to one of them. So C will, in the examples that we will do, algorithms that we will do, C will be a subset of D, but this is not always the case. But what we definitely want is that the size of C is much less than the size of D. So why is this useful? Well, as you can imagine that, given the two constraints that the size of C is much less than the size of D, and that the result of A on C is more or less the same as the result of A on D, this seems like I could really be running A on C and give you the result. That's enough. Okay, let's see. Is this even possible? Let's see a very simple setup that we have all seen in our undergraduate classes. Suppose we are solving an over-constrained linear system. An over-constrained, right, but satisfiable linear system. Right? So we are trying to solve Ax equal to B, and we are guaranteed that there is a solution for now, let's say. Right? So we have that the number of constraints is so let me just figure out where my okay, here. Oh, I see. Let me just convert this to a pen. So we are seeing, so we are so we are mentioning each of these linear equations as constraints, and we are saying that these are the variables. These are the variables, and we are in the setup where n potential is much larger than d. Okay? And here, and we all know how to solve this. We do Gaussian elimination, etc., right? So one interesting thing to note, and this is easy to sort of understand in hindsight, of course, is that we don't need all these n linear equations, right? I could have done with only d of them. And in fact, right, I can, this has come over from a later slide. Don't worry about this one right now. So I can solve this by Gaussian elimination, and I can sort of, I only need d of them, right? But which d of them do I need? I only need d of them that are linearly independent, right? So if I could find these d linearly independent equations, I would have solved Ax equal to b, right? Using these d linearly independent equations only. However, right, how much time do I need to find out these d linearly independent equations? Right? And sadly, that time itself is quite significant. It's of the same order as the time required to solve the original equation. Okay? Let's go even further. Right? Let's see that. I mean, can I generalize this? Let's generalize to a more general over-constraint system, right? That it might not be a consistent system. So now I now have Ax minus b, right? And we're trying to find x that minimizes this error. And we are still in the setup where n is much larger than b. Okay? And we're trying to find x that minimizes Ax minus b. So whatever norm, right? I can use 2 norm, I can use some other p norm, etc., etc. Okay. So now here's the question again, right? Is my previous intuition true? Can I find a small number of constraints out here, small number of rows of A, because constraints are really the rows of A, right? That gives me a close enough solution. Right? In the previous simple example, I could give you the same solution. Now I'm even asking that, can you give me the close enough solution to the solution that you will find by minimizing over the full data? Right? Is that possible? Number 2, right? And is that possible to find these efficient, to find out these small set of constraints efficient? Let's see. Okay. Very surprisingly, the answer is yes. Right? And the answer is yes, not just for the 2 norm. Answer is yes for a bunch of different norms. These are called LP norms, and for all p greater than or equal to 1. And in fact, very surprisingly, that's the structural result, even if you're not worried about the algorithmic part of it, that it's possible to find out about d to the p such rows, right, that are linearly, that basically characterize the solution. By that, what I mean is that if you solve this d to the p cross d system, right, you will get it's possible to find out such rows such that you are guaranteed that the resulting solution will be very close to the solution that you will find by solving on the full data. Okay, so I will sort of describe this in a little more detail later. In fact, we will sort of augment on this. Okay, so how do I formalize this? How do I formalize this? I mean, how do I find out these rules? So in order to do this, we need to formalize all of these problems, right? And here formalization that was developed by Langbach and Schulman, it's called a query and cost perspective. So this is a general way of looking at a bunch of optimization problems. A whole range of optimization problem fits into this perspective. Here is what I mean. Let's say that we have an optimization problem, and let's say that capital Q is my space of solutions, all the possible solutions. Okay, so each such solution I'm denoting as small q. It's one of the proposed solutions. So this is generally termed queries in this Coreset literature, right? So what are some examples? Let's say in the regression setup. In the regression setup, if you are solving Ax minus b, right, then the x is a proposed solution, and that's what I'm calling a query or a proposed solution, right? When you're doing clustering, right? If you're clustering a bunch of points, right? Suppose you're doing a center-based clustering, either a k-center or a k-median or k-means. These are called center-based clustering. And in case of clustering, one proposed solution is a set of k-centers. Right? This set of k-centers is a proposed solution. And what the algorithm really needs to do is find out the best such proposed solution. Okay, and how do I sort of write out all of these costs, right? So the total in all of this, the total cost f of q. See, remember, q is a proposed solution. So I'm writing out the cost for a proposed solution can be represented as an aggregation over the different points. Okay, so what is a point? In the case of the regression, we can say that one row of A, right, and the corresponding label of B, right, kind of defines one particular point, right? And because the total cost of the regression, I can write it as AQ minus B 2 norm square, which is basically the same as writing summation over all I AI transpose Q minus BI 2 norm square, where AI is one row of A and BI is the corresponding element of B. Okay, so this is the sum is then the aggregation over all the possible rows. This is a summation over I. Right? If it's a k-means clustering, right? I mean, even then you can kind of look at it as the following: that I take the proposed solution, which is basically a set of centers, k centers. Then I find out what is I associate every point with one of the k centers, right? And I find out what the distance of xi from this set, right? Basically finding out the closest center to xi. And then I square it if I'm doing a k-means, or I take just the distance if I'm doing a k-median, and I sum over all. So this is I take the cost of a single point and then I aggregate over the different points. If it's a k-center, then the aggregation represents a maximum over all I rather than a summation for all I. Okay. So basically, my point is that a lot of such problems can be represented as a sort of in this abstract query, and then pointwise cost, and then the aggregation of this pointwise cost kind of setup. Okay, so we will talk about it in that setup. So, I mean, we saw these examples in the k-median or k-means. The query is a set of k-centers, and the function, the cost of a single point is really the square distance of xi to the nearest center in Q. In case of linear regression, the query is a proposed vector, and the cost of a single point is xi transpose Q minus B, or AI transpose Q minus B. Okay, what do I mean by strong coreset? Here is what I mean. Okay, that suppose we are saying that capital X is your original data set and Q is a proposed solution. The total cost FQ is being represented as an aggregation, and the coreset now is a weighted data set, right? And I will denote this as Xi and the corresponding weight Wi, right? So the coreset cost of Q, right? Basically, the cost of the query Q when evaluated on the coreset is nothing but the summation of Wi times the pointwise cost. So take the pointwise cost of the ith pointwise cost and multiply it by Wi, and then you aggregate over the coreset. So this is the coreset cost of the solution. Okay, and here is what we want. What we really want from the coreset is the following. What we want is that given a data set X, I want to say that I want a coreset C. Remember, a coreset is a set of points and the corresponding weights. I want a coreset C such that for all possible queries, for all potential solutions, I want to say that calculating the solution on C is a very good approximation of calculating the solution on X, right? That f of CQ is within 1 plus epsilon f of x cube, or f of q. I've denoted that for brevity, and at least 1 minus epsilon fx cube. So epsilon will be a user-specified parameter. Of course, epsilon will control the size of the coreset that you're interested in. And we want to say that we want to achieve this with probability 1 minus delta. So I'm talking about a randomized approximation algorithm here. And that's going to be, and this is a kind of guarantee that I'm looking for. So why, right? First of all, why? Second of all, how? Because, I mean, why do I want this? Because it's not hard to show, right? And I'm not going to go into the details of it, that if I have this kind of strong guarantee, that helps me with the following problem. That now, because for any potential solution, the cost on the coreset is similar to the cost of the full data, might as well optimize on the coreset. And that will give me basically a 1 plus order epsilon approximation of optimizing on the full data. That is why I want such a strong guarantee. Second of all, how, right? Because now we're talking about all possible queries. So even for the simple examples that I gave you for regression or for clustering, set of all possible queries is infinite. So how can I possibly say something for a infinite set of queries, right? I won't be able to take union bounds. I won't be able to do anything smart. So what can I do? So I mean, so answering the why question here, I'm not going to go into the details of it, right? So this is called a strong coreset. But just to summarize, a strong coreset implies a good approximation, right? And I'll share the slide if you want. Just take a look at the slides. Basically, if you have a 1 plus epsilon strong coreset, then what you can guarantee is that if you find out q tilde, right, which is an optimal solution on found using only the points of the strong coreset, and if you evaluate q tilde on the full data, basically if you calculate what is fx q tilde, right, you can guarantee pretty easily that fx q tilde is not more than 1 plus 3 epsilon fx q star, where q star is the optimal solution calculated based on the full data, and that is basically the smallest value. So fx. So I've sort of dropped the notation, some notation here. Right? So we are saying that fx q tilde is less than 1 plus 3 epsilon fx q star, right? Which is pretty nice, right? Because epsilon is a user control parameter. So basically it's saying that I can go as close to the optimal solution as I want, as long as I'm willing to make my coreset sort of correspondingly scale with epsilon, of course. Epsilon is going to affect the size of the coreset. Okay. So a bunch of related threads were not exactly the same. So I mean, for those of you who know, I mean, there's a entire literature on sketching, right? Sketching is basically a randomized summary of the data created using through linear transformations, such as projections. The differences are the following. The transformation that we do in sketching is data oblivious, right? And we don't keep the original data points. We keep the linear combinations of the data points, right? And how that matters is that we might lose sparsity. For instance, it's possible that the original data was very sparse, but because now we are doing linear combinations of them, we might not remain sparse anymore, right? And that might affect my resulting computation, at least the complexity of it. Sketching has a plus point that it supports easy updating. Inserts and deletions are pretty easy to do. There are a bunch of other subset selection strategies, namely the one that use nice combinatorial properties such as a modularity that use a validation data set and thereby I mean, say that, okay, out of my training data, what is the best subset of my training data that minimizes the loss on my validation data set, right? These don't come with strong theoretical guarantees as the one that I was showing. Basically, you cannot say something about all possible queries, and you don't get a 1 plus sort of epsilon kind of an approximation that we do. There's the other field of property testing, in which you don't look at the data, right, completely. You're allowed to sample the data, you're allowed to poke at the data, and you're asked, and you need to answer questions on the data in sublinear time without looking at the entire data set. So all of these there's connections with all of them, but they're not exactly the same. So how do I create the coreset? Okay. So here is I mean, there are a bunch of different methods, right? I'll focus on only one method in this talk for for time's sake. Right? Here is how what we'll broadly do. What we'll say is that we create the coreset out of a smart sampling strategy. Right? And the sampling distribution will be carefully designed. Let us denote pi to be the probability of sampling the ith point, right? And if sampled, right, then we sort of scale the point appropriately so that it sort of keeps the cost function unbiased, right? Because if the sampling is if the point is sampled property pi, then I will scale it with some function of 1 by pi, right? So that the resulting cost function remains unbiased. For instance, in this particular example, if f of aiq is ai transpose q to the power p, and ai gets sampled with probability pi, right? Then I need to scale the contribution of AI. I need to give a weight to AI, which is equal to 1 by pi to the power p. Right? You can easily calculate that in this case, this is an unbiased estimator. So the big question is the following, right? I hid everything under the rug. How do I then design the sampling probabilities? Because that's simple, because that's the entire thing, right? Here is a beautiful framework by Langberg and Schulman that was developed initially by Langberg and Schulman and further developed by Feldman, Bregman, Lang, Stratman, and Zoe in 2016 that says the following. That look, right? Define what is known as the sensitivity of every point. What is the sensitivity of a point, right? I'll go over the formulation, but here is what it means in English. Right? You can kind of interpret it as the following, right? That is there a particular query or a potential solution in which this point's contribution to the total cost, right, for this potential solution is large, right? I'll repeat that again. Is there, let us say that, let us calculate the fractional contribution of this point to all potential queries, right? The fractional contribution out of all the points, right? That I contribute 1 by nth fraction, you contribute 1 by 10th fraction, etc. of the total cost. What is the, is there a query for you for which this fractional contribution is large? And the maximum of these fractional contributions is what I define as your sensitivity, right? And this is what we will interpret as the probability of sampling a particular point. It won't be exactly the sensitivity; it will be some function of the sensitivity. Notice, right, that for every point there can be a different query, right? That makes it achieve its sensitivity. That is perfectly fine. Notice also, I have not told you that how easy it is to calculate the sensitivities, right? We'll come back to that. Okay. But what we will do is that we will calculate, suppose we're able to, imagine for now that we're able to calculate the sensitivities, we will sample points with probabilities proportional to the sensitivities, right? And that will be a smaller subset, right? And I will be able to guarantee, I need to prove theorems in order to guarantee the size of the subset. I need to prove theorems in order to guarantee that the subset satisfies the conditions that I desired. Okay, so again, we won't be able to go into the proofs, but why might this work, right? What is the intuition? Okay, so basically the basic intuition in proving all of this relies on the following. That for under any set of properties Pi under fixed query, you consider the variance of this estimator FCQ. See, FCQ is then becomes an unbiased estimator of the cost of Q on the full data. So consider its variance, right? It turns out that choosing Pi proportional to the contribution that the point Xi has on the of the total cost, the contribution that Xi has to the total cost, if I choose Pi proportional to that, minimizes this variance. Right, and Pi and taking Pi to be bigger than the sensitivity of I bounds the variance for any fixed query Q. Okay. Now coming back to the other point that I left blank, but we needed a guarantee for all possible queries. Right? How do I deal with all possible queries? So for those of you who know a little bit of learning theory, this is not very new, and this is exactly the same framework. What we need to say is that we basically need to cover an infinite space by construct an infinite space of queries by constructing what is known as an epsilon net, right? Which is basic. Think of it as the following: that you are covering the entire plane by tiling the plane in some sense. Overlapping tiles is fine. By tiling the plane, and you can cover the unit ball by using only a finite number of tiles, and you need to prove union bound over these tiles. Basically, that's it. I won't go into the details of this because none of this is our work. Okay. The basic thing to take away is the following: that the total number of coreset, the size of the coreset that you will need because of running through this proof machinery will be proportional to two things. Right? It will be proportional to the total sensitivity of the points, and it will be proportional to what is known as the VC dimension of the query space. The VC dimension of the query space is basically a measure of the complexity of the query space, and the total sensitivity of the points is basically a measure of the function that you are optimizing. It depends on that. Of course, it will also be a function of the epsilon, which is basically your degree of approximation, and delta, which is your confidence. Okay, but how to estimate sensitivity? Estimating sensitivity seems to be as hard as solving the problem. Luckily, there are ways out, right? And any upper bound on it will work. And for certain problems, we can kind of analyze the problem structure in order to find out this upper bounds. And that is why we still have so many papers on coresets in order to bound the sensitivity for each of these individual points. And that's where the devil in each of these proof techniques are. Okay, so let us not go into too many details of it. Some properties of coresets, some nice properties of coresets are if you have P1 two data sets P1 and P2. If you have C1 to be an epsilon coset of P1, right, and C2 to be an epsilon coset of P2, then the C1 union C2 is an epsilon coset of P1 union P2. The epsilon coset, I mean that it satisfies that 1 plus epsilon, the 1 minus epsilon guarantee for all possible queries. That's what I mean by epsilon coset. They also satisfy certain nice properties called composability. If you calculate a C1, if you calculate, C1 to be a delta coset of P, if you calculate C2 to be an epsilon coset of C1, then C2 is a epsilon plus delta coset of P. Right? It's basically, you can keep on calculating cosets and by using this approximation factor sort of pile sum. It's also possible and cosets have this other very nice property that you can convert, that once you have a coset of a particular offline problem, you automatically have a small space streaming algorithm for that problem, right? Basically, here is what here is the guarantee that if for a particular problem you have an offline algorithm to create a coset of size C epsilon, what you can then guarantee is that you can use the same coset algorithm to kind of give a streaming algorithm that uses only order C epsilon times log n space, right? And you can do this by using this kind of branching, this kind of merge and reduce kind of a bound, merge and reduce kind of an algorithm. Right? Basically, create a coset, create another coset, merge the two cosets, and then keep on doing it. Okay, so here is the roadmap for our problems now. We will first talk about tensor factorization and cosets for that. Then we'll talk about Bregman clustering. Let's see. What is a tensor? Any questions, by the way, until now?
So I have one question. This is Vaibhav. So you, in the definition, you want that you have the definition of that coreset in terms of that epsilon, right? Upper bound and lower bound. And you want it to be satisfied for any possible query. But why not restrict that to only queries that are close to the optimal queries instead of doing it over the whole infinite dimensional space? So
that's a very good question. That's a very good question, right? That is still a direction of open research. If that is whether that sort of reduces the size of the coreset significantly. Right? I don't know of a single example yet where that reduces the size of the coreset significantly, right? And so the basic idea, the basics point when we are stuck, I'll tell you is the following: that the solution that you find from the coreset, right, is the optimum solution that you find from the coreset. Now, Q tilde is still a random variable which depends on the random sampling that you did when you created the coreset. Okay. So if I have to say anything about Q tilde, right, I cannot rely on the coreset being a random distribution. I cannot rely on the coreset's randomness anymore because Q tilde depends on this randomness itself. So that's why if I have to say something about Q tilde, I have to sort of, in the proof that I did not go over, I have to be able to say something about all possible queries. But you're absolutely right. I think it is possible to modify this to say that if you are two approximation for all queries that are two approximation, only then you have a strong coreset. Yes, it's a very nice open question.
Okay, and one more question: why is that number of samples proportional to the sensitivity in some sense?
Okay. So in some sense, so the operational way that this happens is that we have the sensitivity of every point, and we sample this point with probability proportional to its sensitivity, right? And that's why in the expected number of samples, the summation SI comes in. So this is the operational reason.
Okay, thanks.
Okay. So let me talk a little bit about tensor factorization and the cosets for that. So what is a tensor? Well, a tensor is basically a multi-dimensional array. That's one view of it, and that's really the view that we will take. I mean, I'm not going to talk about tensor as an operator, right? It's useful in many settings such as signal processing, right? And why do we talk about tensor factorization? And here is a very nice nice reason behind it, right? Note that a matrix low rank decomposition is not unique. Right? Because if I were decomposing a matrix A, right, as Q times R, I might as well decompose it as Q times T and T inverse times R for any T that is invertible. As long as T is invertible, right, I can also write the following. Okay, we will see that this is not doable for matrices, for tensors, right? A tensor decomposition has certain uniqueness properties, right? And that is one of its attraction. Okay? So, but first, let me show you what is tensor factorization, right? Here is what, right? Here's the most basic thing. Suppose I have, think about a three-dimensional tensor, right? And basically a cube, right? And we can kind of write it as an outer product of, maybe we can write it as an outer product of three vectors A, B, and C, right? This is what I will say is a rank 1 factorization of this particular tensor, right? Now, what is a rank K factorization? Well, it's like I mean the same intuition as you would do for a matrix. Basically, you write it. Can you write the tensor as a sum of rank 1 outer products? If you can write it as a sum, as a k sum of rank 1 outer products, I say that is a rank K decomposition of the tensor. Basically, it's a sum of rank 1 tensor, K rank 1 tensors. I approximate it by a sum of K rank 1 tensors. Okay. So why is this useful? Right? Oh, so first of all, here is the nice theorem I was talking about, and this was by Kruskal. What he proved is that under a very sort of simple set of assumptions, right? This decomposition is unique, right? Basically, you cannot do the trick that you were doing with matrices. Right, even for a mode 3, even for a three-dimensional tensor, this called a CP decomposition, the canonical polyadic decomposition, is unique under mild assumptions. So how do I calculate this? And the way to calculate this is basically very similar to the way you would calculate a matrix, a matrix's eigenvalue decomposition. Right? What you do is the following: you define what is known as a sort of a sort of product of a Q, let's say, tensor compression, right? You define the product of this vector Q, which is basically you're making K copies of Q, and you define the product with the tensor K as summation of all possible AI transpose P. Oh, I did not write down that. Suppose T is composed of A1 plus AN. Basically, supposing T is a matrix of this form, right? Basically, it's a matrix where A1, you have taken the K outer product of the vector A1, the K outer product of vector A2, and the K outer product of vector AN, right? Then you define the tensor product of Q with just this technical name is missing me, what it's called. This TQQQ as summation of AI transpose Q. It's basically just like as you would do for a matrix, X transpose AX is summation XI XJ AIJ, right? That's the same thing that you're doing out here. Okay, anyway. So now, and what you then do is that in order to find out one of these, the first one of these decompositions, you find out the Q that maximizes this quantity, right? And then you say that this is my rank 1 factor, right? And then you peel it off from the tensor T, and then you run this computation again, and then you find out the rank 2 factor, and then you keep on going. Basically, it's like finding the first eigenvector, the first and the second eigenvector, etc. of the matrix. Okay. What are some applications of tensor factorization? Here are some applications. It's applied in order to create in topic modeling, right? Because basically, think about what is a p-ordered tensor, right? What is a 2-ordered tensor? 2-ordered tensor is nothing but the covariance matrix of the data, right? And we all know that the covariance matrix is very useful if you are trying to calculate, for instance, the PCA and the low rank approximation of the data. Similarly, right, a p-ordered tensor, right, can be used to calculate, is basically capturing the pth moments of the data, right, and that can be used to, and the low rank factorization of it is gives us basically gives us the topics, the topic distributions for the documents. This is what was the result of Anand Kumar and all, right? That if I'm looking to get K topics that explain my data corpus, what I would do is that I would create a p-ordered tensor, p is equal to 3 is enough, and then I would do a ranked decomposition of this moment tensor. This is called a moment tensor, right? And the same strategy has been used to train neural networks, that optimizing certain 2-layer neural networks can be written as calculating tensor factorizations. So here's the brief overview of the document modeling. That suppose I had a document where each document is modeled as being generated from a topic distribution, mu1, mu2, mu So think about each mu(i) as a mean of that corresponding probability distribution, and wi is the probability of the ith topic. So think about the document, every document as basically a vector over the set of terms. So how do I want to learn the topics mu1, mu2, mu because each mu(i) is really a probability distribution over all the words. So what do? I can, given the documents AI, each document is being represented as a vector of the words. If I were interested only in calculating the covariance matrix, I calculate this matrix M2, which is the tensor of AI with AI itself, right? And a third order tensor could be AI tensor, AI tensor, AI. That's the third order moment. Then all that I need to do is that in order to find the topics, is that I can factorize this moment tensor M3, right? And the factors that I will get will give us ideas about what the original topic distributions were, or the original sort of original mu(i)s were, right? And why is that? Because if you write down the expectation of this moment tensors, it's not hard to see that that the expectation of the second moment tensor is basically mu(i) tensor mu(i), where I ranges from 1 to k over all the topics, along with the corresponding weights that you have in your generative model. And the expectation of the third order moment tensor is basically mu(i) tensor mu(i) tensor mu(i), right? Therefore, you don't really have this expectation M3 matrix, but you have the M3 matrix calculated from the data, right? And if you factorize this, right, you will get some idea of what these mu(i)s are. And this is where the uniqueness of the tensor factorization comes into play, that you really get the actual mu(i)s. Anyway, we'll not go into too much details of that, but here is the computational issue. Computational issue is that if that in order to create the pth order tensor, moment tensor, right, I need to spend time which is order n times d to the p, where n is the number of data points that you have, and d is the dimension of every vector, and the size of every vector. And the space is order d to the p, because it's a pth order moment, a pth order tensor. Can I reduce the time complexity of this? Because this time complexity is huge, right? Can I use a sample of these documents, right, in order to create the moment tensor? But again, I want to be able to guarantee that even if I'm using the sample of documents, right, and trading this M3 tilde, if I want to be able to say that if I factorize M3 tilde, I should be getting back the same kind of topic distributions, the same kind of factors I should be getting out of M3 tilde as I did out of the original M3, right? How do I guarantee this, right? So the way to guarantee this is the following. I want to say, and here is what we will say. We will say that suppose we have a set of n vectors. Think about this as the documents. Each of these are d-dimensional that are coming in the streaming fashion. Right? And I want to say that, can I choose a set of m vectors out of it? Right? We don't want to choose all the vectors, and I choose only m vectors out of it. And suppose I want to say that that if I choose and C is the set that I choose, and I want to be able to guarantee that if I calculate the pth order tensor from C, right, factorization of that will give me the same kind of factorization as the factorization of the entire data set. And for that, let us say that here is I will sort of guarantee even a lower order thing. I will say that if I do the pth order tensor contraction, this was the term I was looking for. This is called a tensor contraction with a particular vector. I want to say that for all possible queries, doing the contraction with respect to the coreset C is not very different from doing the contraction with respect to the full data A. Basically, the error between these two is bounded. Right? This is can I guarantee this? And I want to guarantee this for all possible queries that lie in some k-dimensional subspace, right? Because I'm interested in calculating only a rank k factorization, right? But for some fixed, until some k-dimensional subspace, I want to be able to say that this tensor contraction, that calculating the tensor contraction with respect to the coreset is equivalent to calculating the tensor contraction with respect to the full data. Okay. So can I sort of do this, right? Here is, how do I measure how well I'm doing, right? And I'll introduce 3 different measures. I'll say that, look, right, you have said that the documents are streaming and coming to you one by one, right? So let's say that here are the 3 different resource issues you should be worried about, right? Number 1, you should be worried about what is the size of your course set, which is how many points that you need to store in order to ensure this. How much working space do you need? Because even to decide whether to store one particular point, right, you need to do some computation. And because it is streaming, the working space is the main issue. So you need to be worried about how much working space that you need in order to do this. Number 3 is that, again, because it's the streaming thing, right? When a new point comes, you need to be you need to update your set quickly. And you need to decide whether to take this point into your course set or not quickly. And that's what I call update time. How small can we make this update time, right? And the reason I'm pointing this out, because this problem is not entirely new, right? Because there have been algorithms for this problem. Those people have looked at in the offline setting, but as we mentioned, that any offline course set can be converted to a streaming course set using this merge and reduce framework that I mentioned, using this tree building framework that I mentioned. And for each of them, we can kind of calculate each of these resource usages. What is the size of the course set? How much working space is the algorithm using? And how small is the update time? And it turns out that okay, it turns out that this guarantee that we want for the tensor contraction is very similar to a set of guarantees that people have worked on called for LP subspace embedding. Basically, that we are reducing the size and that we are embedding a set of points, right, from a high dimensional subspace to low dimensional subspace, and we want to measure the error in the LP norm, right? So so these 2 problems are very related, it turns out. Right? And so we can basically sort of take as baselines everything that people have done for LP subspace embedding and sort of see how these algorithms are performing in our setup. So let's see. And here are the 3 axes that we're comparing the algorithms on: the sample size, the update time, and the working space, right? And these are algorithms either for tensor factorization directly or for the LP subspace embedding. And we had a set of algorithms back in 2009 that takes that sort of create code sets of size d to the p k epsilon square, because when we want to do a rank decomposition, remember, we want to do a rank decomposition of the tensor. Okay, so the core set size that you need to keep is d to the p times k times epsilon square. Update time is pretty large, d to the 5, right? And the working space also is significant, d to the p times k epsilon square. But d to the p sort of might be needed, right? Because all of them seem to need something of the order of d to the p, except this, which is of the order of n to the gamma, right? There have been other modifications to these algorithms that have various that kind of play against each other, try to reduce either the sample size or the update time or the working space. I mean, I don't want to go into the detailed analysis of these algorithms. Basically, each of them is pretty big in at least one of the in one of them. Either the sample size is pretty big, or at least update time, if you see, right? Other than this, everybody else has a huge update time, right? Basically impractical update time. So can I do something out here? Can I reduce the update time much more without penalizing the sample size or the working space? Turns out that you can, right? And this is what we looked at it. What we said is that, well, look at it as sort of a online problem, right? In this sort of automobile manufacturing kind of machining kind of way. What we will say is the following. So by online problem, I mean the following. By online problem, I mean to say it's kind of more restrictive than a streaming problem. What you need to do is that when a data point is presented to you, right, you need to decide at that point, right at that point, whether to keep the data point in your course set or not. If you say no, then you cannot take it anymore in the future. If you say yes, then you have to take it in the future. You cannot throw it away in the future. You have to take it. Okay, this is what I mean as an online problem, right? What we say is that look at this as kind of 2-stage filters. The first one, we call this a line filter. What will the line filter do? The line filter will be a very fast algorithm. It will have a small update time, but it won't be a very good algorithm in terms of the core set size. It will only throw away, it will throw away n minus n into the delta rows, and it will keep into the delta of the data point. So into the delta is still pretty big, right? It's bigger than any one of the baselines that you see, but its update time is very small. And it will preserve the epsilon coreset tensor contraction guarantee. The second one will be a more expensive algorithm. It will be a kernel filter, what we call a kernel filter, and this will be more expensive. It will have higher update time, but it will be able to. It will only work on this into the delta filtered rows, right, and give me a much smaller coreset, right? That will obey this coreset guarantee. Okay, basically it's a mixture of two lemons that give me this lemonade. Okay, that one of them is a fast algorithm, right, but doesn't throw away very many points, throws away a lot, but not significant enough. The second one is a much slower algorithm, but it really reduces the size of the course. But notice that because the second one is only working on into the delta data points, because it only receives into the delta data points. Therefore, the average the amortized update time is really controlled by the first algorithm, right? So the first algorithm is really fast. That's what is going to be the intuition. So let's see what are the algorithms. What we will do is that we take these incoming vectors, we'll process this each incoming vector, and then we will calculate we'll calculate their orthonormal basis, and then we will kind of use this orthonormal basis, the norm of this orthonormal basis, and then do this filtering. So again, I don't have time to, unfortunately, go into the detailed proof of this. This is the first algorithm. Okay. So this what this will do is that it will kind of look at the norm of this, calculate the orthonormal basis UIs of each of the data points, look at the pth norm of this orthonormal basis, and then sample with probability proportional to that. And it will have a guarantee that says that it preserves this tensor contraction, right, with update time only order t squared, right? Working space only order t squared, right? But the coreset size is pretty big. It's of the order of n to the power 1 minus 2 by p. So pretty big. Again, okay. So here's the second algorithm, and we call it a kernelization algorithm because it's a kernel. Because what it does is that basically it converts the LP calculation into a L2 calculation in the following way: that given a particular vector AI, it calculates another vector which is basically a tensorized form of this vector AI, right? It calculates it basically. It takes the outer product of this vector with itself p by 2 times and then vectorizes this thing, this tensor, right? And then now what you can do is that you can take these new vectors, right? You can take these new vectors. You can again do the same orthogonal basis kind of a trick on these new vectors, and that will kind of preserve your coreset. That will give you a good set of sampling probabilities. So again, this is the kernel filter. Basically, you calculate the vectorized form of the outer product of the AIs, and then you calculate the orthonormal column basis of the resulting matrix, and then you sample based on these probabilities, and this gives you the coreset. Okay. Okay, so what is the final result? Just the result for this. The kernel filter has an update time which is much more than, remember, the previous one was order t squared. Now we have d to the p plus 1. Working space is also much higher, d to the p plus 1. But the coreset size is much smaller. It is n to the power p by 2, some d to the power some k by k times epsilon square. By the way, there's a typo here. This should have been n to the power 1 minus 2 by p. D to the p by 2 times k epsilon square for odd p. It's so pretty small actually. By combining two things, we're able to get a pretty small coreset size and much faster update time than any of the previous algorithms. Okay, and here is the entire pipeline. We feed it through the kernel field. So the input points are coming, and each input point is first sampled based on the filter through the line filter, and if it sort of passes the line filter, if line filter decides to keep it, then we kernelize it, basically calculate the outer product of it p by 2 times, then vectorize it, again do a sampling based on the resulting orthonormal basis, and then decide to keep it in the coreset. Okay, that's the resulting steps. Okay, so this is our algorithm in comparison to the previous ones. You could just focus on these two results. It says that the running time is d square amortized as opposed to everything else that was previously. This is the only one that is faster than us. However, their E is much their coreset size is somewhat larger than us. And everything else is and all the previous algorithms are significantly slower than our sort of update time. Okay, so we also ran these experiments and ran a bunch of experiments on this. And because I want to talk to you about something else, I'm not going to describe all this all the results. But basically, it performs very nicely. It performs very nicely. It beats a bunch of the existing baselines. Okay. Let's not go into the Bregman clustering right now. Let's skip this. I only have 10 minutes. So, okay, let us talk about something which is easier to sort of get in this 10 minutes. I was talking to you about optimization problems, right? And I want to ask that suppose I regularize my optimization problem, right? For instance, I in the least square regression, I add in a regularizer, let's say the ridge regularizer. What happens to the coreset size, right? That if I had a coreset size, that was derived from a normal linear regression, will the coreset size for regularized regression be smaller than that? Intuitively, it should be, because see, what does the regularizer say? The regularizer says that, in some sense, says that don't focus too much on the data. Right? Believe in your prior a little bit more than what you were doing previously, right? And what that says is that the effect of the data is a little bit reduced, and therefore you should be, your coreset size should also go a little bit down, because it does not depend. Your optimizer, has a little less dependency on the data. And it turns out that for ridge regularization, yes, that is true. You have to design a new set of sampling probabilities, but yes, you can show that, at least for linear regression with ridge regularization, you can prove that the coreset size is definitely smaller than provably smaller than the coreset size for normal regression. However, how about for lasso, right? Lasso is another regularizer, which is basically lambda times x1, right? The one norm of x. Right? This also has the same intuition, right? Because we are believing in this kind of a prior, and then we're giving some weight to this, right? So does the coreset size reduce? Very interestingly, it does not, right? While there was a previous result in 2016 that says that for ridge regression, the coreset size is definitely less than the coreset size for the original data. For other this problem had remained open for a few years, and what we show is that for lasso, there is no smaller coreset. Right? In particular, you need to satisfy the regularization, need to satisfy a certain set of conditions if it has any effect on the coreset. Right? How about other kinds of regularization? Right? For instance, look at the problem of fairness of coming up with fair classification or fair regression problems. Sometimes what we do is that we apply regularizers on these problems, and these regularizers are interesting in the sense that they're inherently different. They're not norm-based regularizers. They're constraints that are based on the data. For instance, we need to say that if we are coming up with a fair credit card, sort of fair credit score, right? I need to be able to say that, okay, it's not going to look too much at the gender. So I need to be able to sort of add in a constraint that says that your credit score sort of prediction algorithm that does not differ too much between the male section of the population and the female section of the population, right? And that can be affected by that can be implemented through a regularizer. But it is not the kind of regularizer that we have been using before, because it has to depend on the algorithms that are output on this data set, right? And what it means is that these regularizers cannot have a different kind of property that the solution set also changes with the subsampling, right? Because if I subsample a sort of coreset, if I create a coreset which has some male and some female, right? The feasible solutions that is ensuring that on this coreset, right? That is ensuring that the credit scores of the male and the female have come from the same distribution. The feasible set differs in the core set and in the full data from the feasible set in the full data, right? So therefore, building a core set for fairness regularizers is a slightly different problem, right? However, we had a paper that came out in AI Stats this year. Says that you have to redefine this core set property a little bit carefully, right? And using this, you're able to define core sets for a bunch of fairness problems, including regression statistical parity, individually fair clustering, etc. And that dramatically reduces the size of the complexity of this fairness algorithm. Because one of the banes of the current fairness algorithms is that while the formulations might be nice, they're often very expensive. For instance, one of the fair clustering algorithm that's very popular uses time n to the 4, k to the 4. I mean, nobody can use an n to the 4 algorithm practically, right? Using our courses, we're able to guarantee the same thing, but reduce it to time nkd plus order k to the 8. So even then, it might not be entirely practical. However, it's definitely much better. Yeah, and we have done some empirical studies on this. So notice the times out here, right? If you use a 5% core set, right, you take 3 seconds on the full data. I mean, you need 3 seconds to run your algorithm. Using the full data, you need 1400 seconds to run your full algorithm. And if you look at the 5%, so this x-axis is the size of the core set, 5%. So let's say this or this, any one of them. This is the kind of error that you have. So you have about 2 to 3% error if you employ a 5% core set, right? And basically you have a pretty decent sort of fairness algorithm. I mean, that's running in time that is really practical, only in 3 seconds. Okay, so there are a bunch of other algorithms that other works that we have in pipeline. For instance, one of the things that I told you is that we were only creating core sets based on independent sampling. Why is that, right? Am I really restricted to such a framework? It turns out not really, right? In fact, there's this beautiful work by, you might have already seen, on spectral sparsification for the twice Ramanujan sparsifiers by Nikhil Srivastav and others. And it turns out that while that work is for graph sparsification, you can basically take that work and you can kind of sort of utilize the techniques and the proof techniques there to work for core sets also. And that will give you deterministic, what we think right now. So we're still writing out the proofs, etc. What we think right now is that will give you deterministic core sets, right? And it will give you core sets that are independent of the VC dimension of the query space. Right? It will be an iterative algorithm for create core sets. It will not be a sort of independent sampling based algorithm. Right? So your core set creation time might be a little more. However, the core set size will be small, as small as the one for independent sampling. In fact, smaller. And you will get deterministic guarantees. That's a very nice thing. We also have some other results on core sets for what we call non-parametric clustering. Basically, that suppose you want to cluster the data, but maybe you, your friend, all of you want to use a different value of k. It turns out that in the existing core sets, the size of the core set has to depend on the number of clusters. Right? Can I make it independent? It turns out yes, you can. You have to relax the notion of error a little bit more. You cannot do with relative error. You have to deal with additive error. But yes, modulo that, you can build up core sets for non-parametric clustering, and we have some results for that appear in TMLR. Okay, so summarizing, sorry for rushing it through. Core sets is, I feel that core sets is a very successful application of randomized algorithm, both randomized algorithm and computational geometry intuition in machine learning, right? And the work spans multiple communities, right? Computational geometers, machine learning people, etc. There are a few repeated things that come up in core set algorithms, right? Number one is important sampling, and basically building your sampling distribution carefully, right? In fact, building a sampling distribution, one of the very successful things is that building a sampling distribution based on a rough approximation of the data. That you sort of take a rough approximation and then you look at, okay, how much error each point is contributing, right? And then you build your important sampling measure on that. Sort of similar to boosting, right? The technique, not the final claims. right? Plus the clever use of low dimensional projections, etc., is also, also comes into play. It's a very interesting combination of theoretical and non-trivial questions with practical implications, and a number of recent papers show empirical validation of the results. I was also seeing some more recent work on application of coresets to continual learning, right? Where basically, you kind of use the coresets to preserve to keep a small rehearsal memory of whatever you have seen before, so that you don't have this forgetting issue that is there in your continual learning setup. However, there are a lot of open questions. The existing questions are mostly focused on unsupervised setups, right? And they're mostly used worst case data assumptions, right? And therefore, the supervised setup is still relatively unexplored, right? Can we do better than worst case errors? Can we do, for instance, data dependent errors, right? And one of the questions is what one professor was asking, that do we really need strong coresets, right? Do we really need coresets that preserve a guarantee for all possible queries? Maybe not, right? There are other kinds of subset selection strategies based on submodularity, etc. Those come with a different set of theoretical guarantees, right? Can we put them together? Coresets in dynamic settings. What happens for data deletion? What happens in online settings? We have some online coresets. For a lot of other problems, we don't have online construction. So deterministic construction is another big open question, right? There's also some very nice questions related to connections with some empirical work that has been recently done on data set distillation. And since people showed that if you have MNIST data, right, you can kind of create sort of synthesized data sets, right, such that only you need only one image per MNIST class, right, and you can you can combine this data set along with a kind of fixed initialization neural network in order to get a pretty high accuracy neural network. Basically train on a much smaller data set. And then this is still empirical work, very empirical work. So, but I don't know, there might be some connection with this coreset business that I was talking about. Okay, so, and more importantly, I feel that one of the things that is lacking is more practical implementation. That's something that we're also working on, that there should be a library that people are able to use, just like using SciPy, NumPy, etc. And we don't really have that. Anyway, there's also lots of other applications. As I mentioned, there's very interesting applications in privacy, in events, things like fully homomorphic encryption, continual learning. That's something I mentioned. In preparing a rehearsal memory that helps pre-training in order to prevent catastrophic forgetting. We can go over these based on your questions. Here are the references that I used. There's very nice Coresets Omnibus. There's an updated survey by Coresets by Feldman, who's one of the sort of founders of the field. There's a easy to read book by Olivier Bachem, Lucic and Croce, and a very sort of mathematically oriented survey by Woodruff. Very nice. Okay, so questions.
Yeah, so I have one question. In those two different settings, the selection strategy that you presented in the optimization problem, your sampling was proportional to the sensitivity, right? And in the tensor factorization, it was proportional to the, I think, the orthogonal last row of the orthogonal basis. So these two seems very different strategy, but is there
really? Not really. Yeah, not really. Okay. So basically, that's a very good point. What you can show is that in this setup, right? In the setup that I was mentioning, right? Then you can show that the sensitivity. The sensitivity is bounded by the norm of this orthogonal basis, the row norm of the orthogonal basis. That's what I was mentioning, because it is not always that you have. You will have not, I don't know whether for all problems you can get a constructive upper bound on the sensitivity that's easy to calculate, right? But for certain problems you do, right? And there are strategies to do this. Specifically for this problem, we're able to say that. I should have pointed that out. Sorry for that.
Okay, and can you briefly comment on the privacy application? Towards the end, you briefly mentioned
yes,
that.
yes. Let me just say a little bit more. So one of the things is the following, and this is not a very new. This is a pretty old paper from CA standards. In like something like 2011 or something, Feldman and others showed the existence of private coresets. Right? What does it mean? What it says is that you can create subsets of the data that is a coreset, right? And that is also differentially private, right? What does that mean? That because it's a coreset, right? It can answer all possible. It can answer an infinite number of queries. Remember, a coreset is something that that can give you an approximation for all the possible queries. But now what it means is that you're able to answer a whole lot of queries without paying an additional penalty for differential privacy. Because it's not that for every query I answer, I pay another epsilon, right? I'm able to create a single subset that's able to answer a whole range of queries at the same epsilon with a fixed epsilon, right? So this paper shows the existence of these private coresets. It does not really give a constructive algorithm to create this for all possible optimization problems, right? There have been some results, right, for k-means, etc., but those, not all of them are very efficient. First of all, I don't want to make a very broad statement. So not all of them are very efficient, and there are a bunch of open questions. Let me just put it in this. Put it thus. Okay. Does that answer your question?
Yes. Thanks.
Any other?
Thank you, Professor Anirban, for an informative talk.
Thank you for inviting me.
As discussed before, we'd like to remind the audience to subscribe to our Google Groups, which is the mailing list for information on future talks. You can also visit our website for more details. The links have been pasted in the chat box. The link to the recorded video will also be posted on the web page. Thank you and have a great evening.
Thank you.